I do not see Chad, Austin. Yes, Jaron is here. Okay, so I guess that's it. In lab tomorrow, I'm counting on there being lab tomorrow because that's where I want to go over carefully Kirchhoff's laws and practice solving problems with it. Now, at the end of today's lecture, it's a fairly short and material lecture. I hope to have time to start on working on Kirchhoff's laws problems. As you know, there's a snowstorm that initially was supposed to be really big, and now it's supposed to pass farther north of us, and so it won't be as big. Doesn't mean it's not going to hit us, so, you know. The weather report downgraded to only 8 inches of snow is what I saw this morning. So
We should just plan on snow day, just in case.
I figure that's what they're going to do for all the Lincoln grade schools, you know, just in case. But Union College traditionally makes the call like at 5 to 6 a.m. So that's when you'll find out. So, yeah, the lazy part of me says snow day, sleep day. But we're going to first talk about transient circuits. Now, I am going to finish defining both of Kirchhoff's laws before I go into the capacitors. So start with the clicker question we ended last class period with. What law is Kirchhoff's current law a restatement of? Check. Oh. Okay, everyone's answered. Even Chad. Have you read it now? Okay. 01015. Okay, Kirchhoff's current law is indeed a statement for conservation of charge. The charge can't be created or destroyed, so any charge that goes into a node has to leave that node. Remember, the equation we saw was sum of the currents at a node equals 0. But since current is charge per time, that's the same as sum of the charge per time that changes has to be 0. Charge can't change. Okay. Kirchhoff's voltage law is equally as genius. Remember I said Kirchhoff's current law was genius because he took something that was an already understood law and made it into something we use all the time that makes his name famous. Well, his voltage law is the same thing. In fact, we have already used the idea of Kirchhoff's voltage law without even talking about why it would necessarily be true. And it stems from this. Voltage, we've learned, is electric potential, which means electric potential energy per unit charge. And so if I start, let's say right here, and go through the battery, what has happened to the voltage when I went through that battery? It rises because I went from the short line to the long line. That means it went up. And so my voltage rose. That meant my potential energy per charge went up. Now if I go through this resistor, the resistor, of course, is something that resists the charge going through. It takes energy out of the charge for it to go through. So the potential energy drops, the voltage drops. And if I keep going, the voltage is going to drop through each one. And if I get the charge back to the starting point, what should its potential energy be like? It should be what it started at. If it wasn't what it started at, then you could just take that charge and go through the circuit a bunch of times, and the charge gets more and more energy or less and less energy. If it gets more and more energy every time it goes through the charge, you've made yourself a bomb. If it gets less and less energy each time it goes through, you've made yourself a freezer. Right? Neither one of those is a realistic outcome. And Kirchhoff's voltage law is really simply a statement of conservation of energy. That the energy goes up, so this is showing energy on the vertical scale, so it went up when we went through the cell. and then it went down through that little resistor just a small amount, went down a lot more through the bigger resistor, down through the final resistor, and got back to where we started. So Kirchhoff's voltage law, also known as the loop law, says that the sum of the voltages around a closed loop, you have to be a closed loop. What do we call a closed loop? A circuit. The sum of the voltage changes around a circuit has to add up to 0. Or sometimes we draw it like this. Should have put sums of. And that's my mistake. Sum of the voltage rises is equal to the sum of the voltage drops on, once again, a complete loop. So that's Kirchhoff's voltage law. When we talked about finding equivalent resistances, we implicitly used this without having any real fundamental reason for it other than it just made sense. Voltage goes down here, voltage goes down here. Total that went down must have been the sum of the two. Well, this is a law that states that. So it's really very, very basic and obvious. But in order to solve circuit problems, we need these basic and obvious rules. So our second clicker question, what law is Kirchhoff's voltage law a restatement of? Somebody was ready for that one. There's a correct answer in half a second. Okay.
Okay.
Would you change your answer at this point? Okay. The voltage law is conservation of energy. Which one is conservation of charge? The current law, right. So, we've got those down. And now let's turn our attention to the sign conventions. These are very important. Whenever you're working with a circuit problem, you're going to be doing things like guessing what direction the current flows. Sometimes it'll be obvious, sometimes it won't be obvious. And so you're going to guess at the direction the current flows and then assign which side is a positive voltage and which side is a negative voltage so you can use Kirchhoff's voltage law. So, do you remember me talking about the sign convention in the past? No. Okay, the sign convention is simply this. When you put the current arrow with the resistor, the side of the resistor that the current went into first, or where the tail of the arrow is the positive side. The side the current comes out of is the negative side. In lab last week, I just corrected the wires when people had them put in the wrong directions. But if you have the wires in the opposite positions, like for measuring voltage, it'll measure a negative voltage instead of a positive voltage. In the lab that's scheduled for tomorrow, you need to be careful when you're measuring the voltage that you're measuring in the right direction, because it might actually be a negative voltage. If you just say, oh, I'm just going to take the magnitude of the number and not put down the sign, you may be putting down the wrong number. So you need to know which direction is positive according to your drawing, and then measure it that way, and then put a positive if it's positive, if it agrees with your drawing, or put in a negative if it's the opposite of your drawing. So having those signs right is vital. If you don't have them right, you're not going to get the problem right. Now with the cell, just did that a minute ago, and we learned it last Monday? I don't know. The long side of the cell is the positive side, the short side is the negative side. So on this one, the positive side is on the right, this one on the left. In both cases, the long side is the positive side. Positive with respect to the other side, it's more positive. Remember, voltage is always measured as a difference. So in all of these cases, this is more positive than that. Okay, third clicker question. Which terminal has a higher positive voltage in the figure below? Okay. The early answers, I was worried. But those who thought it through carefully came through. And yes, you both changed your answers there at the end. So, we had 14 people say B is more positive than A. How would they come to that conclusion? Those 14 are correct. And the answer is not just because Richard said it. It's because when charge goes through a resistor, it resists the charge going through. So it requires energy from the charge to make it through. So the charge loses energy when it goes through. Hence, if the charge is going from right to left, it had to have higher energy, hence higher voltage, on the side it entered and lower energy on the side it exited. That is the end until we go through all of the capacitors of talking about Kirchhoff's laws. After we go through the capacitors, I'll come back and try to solve some problems if we have enough time. Actually, solve one problem. Capacitors. We learned about physical capacitance. That is, we have capacitance because we are separating and making an electric field and storing energy in either the form of the electric field or the form of the charge separation, depending on which one you want to look at. We can put capacitors in series or parallel. Now I'm going to write the equation for physical capacitance. C is equal to, that's not a K, it's a kappa. There's our equation for physical capacitance. It may or may not help us. We're going to look at what happens if if instead of having just a single capacitor, we put multiple capacitors in series or parallel. And I'm going to start by looking at, well, let's see. Tell me, which one is the parallel circuit? They both have an A and a B. Okay, this one. Yeah, the bigger one. Okay. This one here is parallel. It's kind of easy to analyze what happens when you add capacitors in parallel. Because you see how those capacitors are laid out? If those capacitors were exactly identical, they all have the same separation, and they all have the same area. The area is not so important. This is the separation. By connecting the top sides, what have I done? I fundamentally, in terms of that equation in blue, what have I done by connecting the top sides? I've effectively made the area bigger. I've effectively added up the areas. Now, I didn't change the separations anywhere. I just added up the areas. So that means using our physical capacitance equation, there should be no difference in having the connection up here as if I had just butted these up together so that this was touching this and then this was touching this. And so I should just have the sum of the areas, right? Now this was saying if they have the same separation. But it turns out that's the way it works. The physical capacitance, when I put them in parallel, is just the sum of the areas, and thus the sum of the capacitances. That's kind of a hand-waving argument, but it's a very clear and easy to see outcome. Now let's study it with a more physics-based, mathematical, analytical, instead of looking at it and seeing what seems obvious. So if we do it in the more analytical fashion, I had in the upper picture 3 capacitors. If they're in parallel, what thing was the same for all items in parallel? Same voltage. So for my battery has a certain voltage, and I have they all have the same voltage. So that means charge 1 is equal to, remember the equation Q is equal to VC. So I can measure how much charge, or I can calculate how much charge is going to be on each of those capacitors. Now remember, that's charge that, in effect, when I connected this battery, it moved charge from the negative side through the battery to the positive side. So all of the charge that's on the top was removed from the bottom. Now, notice I say this in a very physicsy way. If I was talking about the actual particles, the electrons, what would be the correct way of describing the electrons? I put the battery on there, and what did the battery do to electrons? It forced them to move from where? Yeah. The positive pole of the battery pulled the electrons off, leaving the positive on the charges, or on the tops of the capacitors. And those electrons were pumped through the battery and deposited on the other side, making it negative. So if you talk about what's really going on in terms of, right, I talk about charge as if there's a positive charge. There's not really a positive charge moving here. It's the electrons that are moving. Electrons were taken off of the top and deposited on the bottom. But these two charges have to be equal because this charge was made by removal of electrons, and all those electrons ended up below. So I've calculated how much charge was moved from one side to the other side of each capacitor. Now, if I'm going to make an equivalent capacitor, that equivalent capacitor must have same charge total for voltage battery. Right, that would make it equivalent. The battery can't tell the difference if it's one or the other. That's the equivalence. So it has to move the same charge if it's going to be equivalent. So that means for a single capacitor, here's the lower picture. I don't think we need to look at the picture at this point. We have the Q total is equal to V battery times C equivalent. But how does the total charge relate to the charges on capacitors 1, 2, and 3 in my first picture? It's the sum. So I have to have Q total equals Q1 plus Q2 plus Q3. So V battery times C equivalent is equal to V battery C1 plus V battery C2 plus V battery C3. And the last step here is the oh so simple. Divide everything by V battery, and you end up with C equivalent is equal to C1 plus C2 plus C3. Which kind of arrangement gave me this sum for the capacitors? Parallel. Parallel. Let me scroll up a little. Parallel. So this was for parallel capacitors. So I'll put a P there now instead of equivalent. The equivalent capacitance is the sum of them. Compare that to resistors. If I had parallel resistors, how did they add? It was the inverses, right? So the capacitors and resistors do not add the same way. Now that was the parallel case. Now let's look at the series case. So separate the parallel and series here. For the series case, what was it with resistors? Resistors in series had to have what the same? They had to have the same current. Well, in the case of the capacitor here, you did have to have the same current while they were charging. It's true. But there's no current once you've reached an equilibrium situation. You only have charge flowing until they're charged up, which is what we're going to study as soon as we finish talking about adding capacitors. So what ends up with, if we look back at my description of the electrons moving, I have that battery that I connected, and it pulled electrons off the top plate, leaving it positive. And where do those electrons go? To the bottom of the bottom plate of the bottom capacitor. So I have positive on the top and an equal negative on the bottom. But what rules did we have for capacitors as far as the charge? Yeah, the charge is going to be conserved, so the charge you take off of one plate goes to the other, and you always have the same charge on both plates. So if the top plate is plus C, or plus Q, then the plate on the other side of that capacitor has to be minus Q. But where did that charge come from? It pulled it off of this one. So it had to pull plus Q off of the second capacitor to put it on the first one. Or excuse me, it had to pull minus Q off, leaving the top plate of the second capacitor positive. Question?
Which one were you pointing at?
Okay. So I had electrons that moved from here into the battery and came to here. So this is negative and this is positive. Now because this is positive, it's attracting electrons. And so electrons that were on this plate were attracted and pulled up here to make this a negative Q1. Or negative Q, yeah, negative Q. But because the electrons were taken from this plate, it ends up with a positive Q, because it's now missing those electrons. So now this one's positive Q. This one here is going to be attracting electrons from here. And so you end up with all of these capacitors will have the same charge. So the rule for capacitors is that Q is the same. So that's not the same as the rule that we had for resistors, but it actually does come from the same fundamental relationship. The two work out to be the same underlying situation. So the capacitors all have the same charge. Using one of Kirchhoff's laws, I can give you a relationship between the voltages. Which Kirchhoff law will give me a relationship between the voltages? His voltage law. Very astute. The voltage law is the one that has to do with voltages. I'm not trying to be silly. So we're going to have the voltage of the battery is equal to V1 plus V2 plus V3 just because of Kirchhoff's voltage law. Now using our relationship, remember for a capacitor it's always true that Q is equal to Vc, then V must be Q over C. So for the battery using the equivalent circuit, I'm going to have Q over C equivalent. That's the voltage on the battery using this relationship, is equal to Q over C1 plus Q over C2 plus Q over C3, where I put in all the Q's are the same. Well, now once again the final step is pretty darn simple. What's the final step going to be? Cancel the Q's. And I have 1 over C series is 1 over C1 plus 1 over C2 plus 1 over C3. Now when I first learned this, which was not in high school physics but in college physics, I was a little baffled just because I thought there should be this symmetry that parallels always add the same, series always add the same. And so it's important to me as a teacher that I go through and explain why we have fundamentally different rules. Right? So it's not just some random, well, I'm going to have to memorize this one, but so you can see it. Now I have, of course, another clicker question. When adding resistors, which configuration results in the highest resistance? So I add resistors 1, 2, and 3. is going to be the highest resistance if I add them A in series, B in parallel, or C, it's the same resistance whether it's series or parallel, or D, there's really no way of knowing. All right, we're all in. Brr. They don't give the same resistance. When you add them in series, it's always bigger than the largest because it's the sum. When you add them in parallel, it's always smallest than the smallest of the resistors. So the correct answer was series. Next one. Same question, but I replaced the word resistor with capacitor. Oh, I didn't change that word, yes. Clearly I took one and copied and pasted for the other. Okay. Well, we did better. We did better because nobody said they give the same. I should have been more careful. Parallel capacitors, you're increasing the area like we saw, and thus you're increasing the total capacitance when you put them in parallel. So for capacitors, putting multiple capacitors in parallel gives you the biggest capacitance. So one of the things you might see in somebody's amplifier system for their car stereo is a whole bunch of capacitors all wired together in parallel to get that maximum capacitance. Come on, forward we say. This here is just a slide that doesn't really add much, but a reminder. If you have something like this, where you have a circuit, there's a bunch of stuff above, a bunch of stuff below. You have to break it down into pieces. So you say, aha, the two on the left are in series. And so you add them in series. And they say, now this series combination is in parallel with the one on the right. And so then you add those two as parallel, and you get your total capacitance. And once again, I can't think of a practical good reason why you would want to have this circuit, but you need to understand how they relate. So that's the entire import of that slide. I couldn't just skip the idea. Now to charging a capacitor. Here's a simple circuit. Notice it has a switch. We call a circuit like this a transient circuit. Let us suppose that I was a transient. What would that make me? What? Okay, yes, you are correct. I don't know why they're laughing at you. It's very sad. One of my classmates from high school is a homeless person who travels from place to place until he gets arrested for stupid stuff. Very sad, actually. It started when we were in high school. He and one of my buddies went out and got themselves liquored up on the beach. Not our beach, but they went to a public beach. And because he was drunk, he urinated in public and got arrested for that. And thus the school found out. And so he was expelled and didn't graduate with me. And he just went on to more and more substance abuse. It's very sad. Very sad. Okay, but a transient would be a person who is moving from place to place, not staying. A transient circuit is a circuit that's moving from one state to another state. So, now, in the case of a transient circuit, just like with the case of somebody moving, you hope that they're only in transit for a certain amount of time and then they become stable again. Actually, if I brought up the web browser on this, I could show you a picture of... Anyway, I won't. So, with the transient circuit, you have that switch to take you from the starting state to transitioning to the ending state. So transient circuits are always going to have a switch, or something that acts as a switch. Then you have, of course, in this case, it's a battery or it's a cell. Right, that's a picture for a cell, clearly. something for the power, and we're going to talk about RC circuits, circuits with both a resistor and a capacitor. Something you might ask is, why didn't we talk about transient circuits when we just talked about resistors alone? The reason is resistors don't have any charge or discharge function. It's just charges coming through, going to slow you down. That's all the resistors do. But capacitors store and return energy. So because they store and return energy, it takes time to build up the energy, time to return the energy, and that's why we have this transient study that we look at. So if you look at this circuit, and let me zoom in just on the circuit, not on the graph. So if you look at this circuit, good. Before you open the switch, when the switch is in this position, how much current is going through that circuit? 0, right. Why is 0 current? I just feel compelled. Okay, so when the circuit's like this, why is 0 current going through? It's not a circuit, right? You have to have a cycle that comes back to the starting point, and it doesn't. So in this case, there's no current. If there's no current, then what's the voltage drop across the resistor? It's 0, right. What's the voltage drop across the capacitor? It's 0. What's the voltage drop across the switch?
0.
We were on a roll. Let's take it easy and say, oh, I'm on white. I wrote white 1, but let's say it's 10 volts here. If that switch is open, there's no current, so there's 0 voltage across the resistor. Remember, voltage for the resistor is VR is equal to IR. And the 0 voltage across the capacitor, for the capacitor, voltage is equal, once again, I always go back to Q equals VC. So V must be Q over C. And the voltage drop across the switch is the full 10 volts. Right? Because you start at one place, you go all the way around, you have to get back to 0. You went up 10, you go down 0 because there's no current. You go down 0 again because there's no charge that you've been able to separate. You've got to have the full amount on the final one. So in this case, we have 10 volts here. And of course, since that side's positive, this side's going to be positive, this side's going to be negative. So that's what the circuit's like before I flip the switch. And it'll stay like that forever. It's unsurprising, right? But when I flip the switch, oops. Come on, close. There. When I flip the switch, suddenly, what's the voltage drop across the switch? It's now a wire, and wires, we assume, have 0 resistance. The truth is, wires, of course, have some resistance. We learned the equation. Resistance is that resistivity rho times the length divided by the area. So the wires do have a resistivity that's not 0, so they do have some. But for our application, 0 resistance, so 0 voltage there. Well, if I have 0 voltage here, the capacitor, how much charge does it have the instant I flip the switch? It's still going to be the same 0. It's going to take time for electrons to leave one side and join on the other and come to the other side. So the capacitor at that instant still has 0 volts. The capacitor's voltage cannot jump when you flip the switch, because that would require an instantaneous charge jump. It takes time for the charge to flow. So I have 0 volts here, and I have voltage capacitor initial is 0. So what does that tell you about the voltage across the resistor? It's going to have to be the full 10 volts. So the voltage resistor initial is equal to 10 volts. That wasn't hard, right? Right? Right. Thank you. Just waiting for that some affirmation. Now, we leave the circuit with the switch in this position for just a short amount of time. Some electrons will have been pulled off of the top side, gone through the resistor, gone through the battery, and deposited on the bottom side. So I will have a small amount of charge that is built up on the capacitor. If I have a small amount of charge that's built on the capacitor, what happens to the voltage on the capacitor? There is some now. It's not zero anymore. So the capacitor is going to start building charge with, as it shows, the positive side on top, the negative on bottom. But if the capacitor builds up charge, its voltage is going up. So if this voltage goes up, instead of being 0, this is like 0.1, then what did that do? The voltage dropped across the resistor. It decreased. So the voltage across the resistor decreases, voltage across the capacitor increases, and according to Kirchhoff's voltage law, the sum has to be the batteries, or if it's 10 volts, it's got to be a battery. You can't make a 10 volt sum. So it's got to be the battery's voltage. But if I now have, let's say we're up to 1 volt on the capacitor. The voltage drop across the resistor is now down to 9 volts. But if the voltage is down to 9 volts, what does that mean about the current flowing through it? It goes down. Because the voltage drop went smaller and voltage is IR, if the voltage drops, the current drops. But if the current drops, the rate at which the capacitor is charging is dropping. So the capacitor's voltage will not rise at a constant rate. It'll rise very quickly initially, but then as the capacitor voltage gets bigger, it rises more slowly. Now, in my calculus-based class tomorrow, we'll do the math on this, because you just have to do an integral. But it turns out that the charge, actually I'll use a lowercase q here, the charge on the capacitor is going to be equal to the maximum charge times 1 minus e to the minus t divided by RC, where t is the time, R is the resistance in the circuit, and C is the capacitance in the circuit. So at time equals 0, the exponential term is just 1, and the charge of the capacitor is 0. And as time increases, the charge on the capacitor is increasing with that exponential function. Now that's the equation for the charge on the capacitor. How does that relate to the voltage on the capacitor?
Directly proportional.
Yeah, it's directly proportional. Voltage is Q over C. So the voltage for the capacitor is V is equal to I ran out of space. And it's not responding to my finger. Okay, so I didn't really run out of space. It was the not responding to my finger that was the problem. Now, what is that little script E? It's the EMF. And why did I use that? Because this picture here actually used that funny E instead, but it's supposed to be the EMF. So the voltage, as it's charging, follows that exponential curve. That exponential curve is the characteristic curve you get when you have the value is dependent on its value. The rate of change is dependent on the value. So, yeah, we'll talk about it more when we get to radioactive decays as well. So this is the equation for the voltage on the capacitor. Now what if I want to know the current? Nobody sees that as a likely outcome? if I want to know the current, I could have come back to this equation. If you look at this circuit, just using Kirchhoff's voltage law on this circuit, Kirchhoff's voltage law says that sum of the voltages on the loop equals 0. And so I just start here. I always start at the bottom left corner when I do Kirchhoff's voltage law, and I just go around in a clockwise fashion. So as I go up, I'm going from minus to plus. That's an increase. So it's going to be an increase of my EMF. Notice the direction of my current arrow. I have to use that to determine plus side and negative side. So that's going to be a drop because of the direction of the current arrow. So minus, and the voltage across the resistor is IR. And then finally, going from plus to minus on the capacitor is going to be another drop. The voltage on the capacitor, which is so here I have an equation that I can solve for the current. So to solve that equation for the current, well, since I have a negative side, I'm going to move IR. I'm going to add IR to both sides. And then I'll have to divide by R to get I. So adding IR to both sides and then dividing by R, I have this. Now, you can look at this and say, wait a minute, don't be an idiot. It's simpler to write it as E over R minus E over R, which subtracts out, plus so this is the same thing, but I prefer the upper form. And here's the reason I prefer the upper form. For any transient circuit, it doesn't matter what kind of transient circuit it is, whether it's inductors or capacitors. For any transient circuit, you're going to have the current is equal to the current you're going to have at, see, I got to get it straight now. At infinite time minus the, I'm putting this in the wrong form, plus the current you start off with times e to the minus t. I swear there's something missing. Yeah, there's something missing. Sorry. I'm just going to start right the way I usually do. No, I'm not going to make a mistake again. I initial okay, that's the equation that will always tell you the current in a transient circuit. You have to determine what the current is going to be just after you flip the switch and what the current is going to be after an infinite amount of time, and then you just put those in. What difference do R and C make? They affect the time that it takes to transition. So we talk about an RC time constant that is tau is equal to RC. Why is it a time constant? Because it has units of time. If you take ohms and multiply them by farads, it gives you units of seconds. And so tau has units of time, and it's a characteristic time. If you go back to the picture at the top of the screen, there, remember, it's not touch sensitive, so I have to do this differently. if you look at this picture, it's marked in units of tau. 1 tau, 2 tau, 3 tau, 4 tau. Why? Because for any choice of R and C, the circuit's going to look the same if you just plot time as a function of tau. But if R and C are large numbers, then that time constant is a long time. So it's going to take a long time for the circuit to change. If R and C are small numbers, and of course it's the product that matters, if it's a small number, then it's going to change very quickly. So that RC time constant is very important for how quickly a circuit can respond. Obviously, I'm not going to have time to work a problem. So here is a picture showing a discharge. What's different about this circuit? Very simple. No power supply. Instead, we're just discharging the capacitor through a resistor. Clearly, you would have had to have something to charge the capacitor before it can discharge. So this is starting with a capacitor that's been charged. Probably you had a more complicated circuit, such as in the flash for a camera. In the flash for a camera, the circuit is something like a battery, capacitor, and the flash. And there's a switch. That's not the eraser. There's a switch here that will switch between here to there. And so normally, like you turn on the flash for your camera, and you might actually hear a little whiny sound as it's charging up. That's because when you turned on the flash for your camera, you turned that blue switch over to the left. And now you're having the battery charge up the capacitor. And actually I say battery, if you buy a little disposable camera, it's just you take it apart, there's a AA battery, a AA cell in there. That's what it's using, it's a AA cell. So it's charging that capacitor. It takes a fairly long time to charge it because the R is fairly large. But then when you take a picture, the switch flips over so the capacitor is directly connected to your flash. And so you have all of the energy that you stored in the capacitor when you charged it up is now dumped instantly. Now, a 1.2 volt cell, you're never going to do anything exciting like make a big arc with it, right? You can take batteries or wires and touch both sides. It's not going to do much because they can't pump the current that quick. But when you have the flash and you short it across, you have all of that energy is dumped almost instantly, and you get the bright flash. So that's a very classic use of a capacitor, of a transient circuit with a resistor and capacitor in it, so you can slowly charge the capacitor and then dump it all at once. You have a lot more charge per second, that is current, available when you dump that capacitor into the flash than if you just connected the flash to the cell, because the cell is limited to its chemical reaction rate. Now, have you guys heard about cell phone batteries that can be charged in like 30 seconds? There's research trying to develop such a device, but it wouldn't be a battery at all. It's what we call an ultracapacitor. An ultracapacitor, which you would be able to charge it very quickly if you have a very little resistance. You would be using that in your cell phone just the opposite of the way this works. You charge it very quickly and then you have it running through a fairly big resistance, so it discharges very slowly in your phone. Of course, there is danger here because you have all of the energy stored in there and it can dump it all at once. So the ultracapacitor can also be an explosive device because it stores so much energy and it can dump it all at once. So there's some safety issues there. And I just have to mention this because I find it absolutely hilarious. There are videos you've seen on YouTube if you put your cell phone in the microwave, turn it on for 30 seconds, it will charge it. And they don't tell you this because they don't want you to know that. They want you to buy your cables. How many people have seen that? Really? You guys haven't seen it? There are people who think about things so small that have stuck their cell phones in the microwave and turned it on for 30 seconds. No, it's not going to charge your cell phone battery. It's just going to, a microwave oven is sending electromagnetic waves back and forth in there. And if you have something that's conducting, you'll be making currents go back and forth in there, and you'll be making your cell phone sparkly and useless to you. So it's just hilarious to me that people actually would stick their cell phone that they paid a few $100s for on contract, stick it in the microwave because they want to charge it real quick. Don't ever fall for that. Okay, have a great day. I'll see you tomorrow unless there's no school.
So I see in the diagram that we have there, we have the positive side of the cell and